Hi, my name is Kaitlyn Sullivan, and this presentation covers my final project for ADTA 5340, which focuses on discovery and learning with big data. In this project, I applied multiple machine learning techniques across several datasets, including both supervised and unsupervised learning methods. The goal of this project was not only to build models, but to go through the entire machine learning process step by step. This includes understanding the data, cleaning and preparing it, selecting appropriate models, evaluating performance, and interpreting the results. Throughout this presentation, I'll walk through each part of the project and explain not just what I did, but also why I made certain decisions and what the results actually mean in a real-world context. This project is divided into several key sections, each focusing on a different stage of the machine learning process. First, I developed a machine learning strategy for a real-world company. This part connects machine learning concepts to real business applications. Next, I performed data pre-processing using a large real-world data set. This step is critical because machine learning models depend heavily on the quality of data. After that, I built supervised learning models, including linear regression for predicting continuous outcomes and logistic regression for classification problems. I also worked with an unsupervised learning model using clustering, where the goal is to identify patterns in the data without predefined labels. Finally, I compared the performance of different models to understand which ones performed best and why. Overall, this project represents a complete machine learning workflow from raw data all the way to model evaluation and interpretation. For part 1, I developed a machine learning strategy for Target Corporation. Target operates in a highly competitive retail industry where companies like Amazon and Walmart are constantly using data and machine learning to improve their operations. Because of this, it's important for Target to adopt similar technologies in order to remain competitive. Machine learning allows companies to make decisions based on data rather than intuition, which leads to more accurate and consistent outcomes. It also enables organizations to analyze very large data sets and identify patterns that would be difficult or impossible to detect manually. Another important aspect is scalability. Machine learning systems can continuously learn and improve as more data becomes available. So overall, the strategy focuses on using machine learning to improve decision-making, efficiency, and customer experience across the organization. There are several key areas where machine learning can be applied within Target. One of the most important is personalization. By analyzing customer behavior, purchase history, and browsing patterns, Target can recommend products that are more relevant to each individual customer. This is important because personalized recommendations can increase customer engagement and drive higher sales. Another key application is demand forecasting. Machine learning models can predict how much of a product will be needed in different locations, helping reduce both stock shortages and excess inventory. Pricing optimization is also important. Machine learning can adjust prices dynamically based on demand, competition, and other factors. In addition, supply chain operations can be improved by optimizing delivery routes and warehouse processes. Finally, fraud detection systems can identify unusual transaction patterns, helping prevent financial losses. These applications demonstrate how machine learning can provide value across multiple areas of a business. In part 2, I worked with the Austin Animal Shelter dataset, which contains over 95,000 records. The goal of this step was to prepare the data for machine learning by cleaning and organizing it. This is important because machine learning models depend heavily on the quality of the input data. If the data contains inconsistencies, missing values, or errors, the model's predictions will also be unreliable. So, before building any models, it's necessary to ensure that the dataset is accurate, consistent, and ready for analysis. This step essentially transforms raw data into something that can be effectively used for modeling. Several pre-processing steps were performed to prepare the dataset. First, irrelevant columns were removed, such as unique identifiers and redundant variables. These do not contribute to prediction and can introduce noise. Next, text values were standardized by removing extra spaces and converting everything to lowercase. This ensures consistency across the categories. One of the more complex steps was converting the age variable from text into numeric values. Since age was stored in different formats like years, months, weeks, and days, I converted all values into months. This allowed the model to interpret age as a continuous numeric variable. I also handled missing values by converting placeholders into actual missing values and removing incomplete rows. However, values like unknown were kept because they represent meaningful information rather than just missing data. After completing these steps, the dataset was clean, consistent, and ready for machine learning. In part 3, I applied a linear regression model to the abalone dataset. The goal was to predict the number of rings, which is used as a measure of the abalone's age. This is a regression problem because the target variable is continuous rather than categorical. The model uses input features such as size and weight to estimate the output. Linear regression works by identifying relationships between variables and fitting a line that best represents the data. This allows the model to make predictions based on patterns observed in the dataset. The model achieved an R-squared value of approximately 0.54. This means that about 54% of the variation in the number of rings can be explained by the model. This indicates moderate predictive performance, meaning that the model captures some important relationships, but not all of them. To further evaluate the model, I used tenfold cross-validation. This method tests the model across multiple subsets of the data, providing a more reliable estimate of performance. The cross-validation score was approximately 0.34, which is lower than the test R-squared value. This suggests that the model may not generalize as well across all data and highlights the importance of using multiple evaluation methods. In Part 4, I used logistic regression to classify whether individuals earn more than $50,000 annually. This is a binary classification problem where the model predicts one of two possible outcomes. Logistic regression is well suited for this type of problem because it estimates the probability of each outcome. The model uses demographic and employment-related features to make predictions. This allows us to understand how different factors influence income classification. The model achieved an accuracy of approximately 0.90, which indicates strong predictive performance. This means that the model correctly classifies about 90% of the observations in the dataset. Cross-validation produced a similar score of approximately 0.89, suggesting that the model generalizes well to new data. One important factor to consider is class imbalance, where one category has more observations than the other. This can influence the model's predictions, but overall, the model still performs well and provides reliable results. In Part 5, I applied k-means clustering to group cars based on their attributes. This is an unsupervised learning method, meaning it identifies patterns in the data without using labeled outcomes. The goal is to group similar observations together based on their characteristics. This allows us to identify patterns and relationships within the dataset that may not be immediately obvious. The clustering results showed that the groups align closely with the original evaluation categories. This indicates that the model successfully identified meaningful patterns in the data. Even though clustering does not use labels, the results still reflect the underlying structure of the dataset. This demonstrates that the model is effective at grouping similar observations together. In Part 6, I compared the performance of different models. Within the abalone dataset, linear regression slightly outperformed the decision tree model, suggesting that the dataset has more linear relationships. Decision trees are more flexible and can capture complex patterns, but they also can overfit the data. For classification within the income dataset, logistic regression performed better than k-nearest neighbors and showed more consistent results. This highlights an important concept in machine learning, which is that different models perform better depending on the dataset and the problem trying to be solved. This project highlights several key takeaways. First, data pre-processing plays a critical role in model performance. Second, different models perform better depending on the structure of the data. Third, evaluation methods like cross-validation provide a more reliable understanding of how models will perform in real-world scenarios. And finally, different models perform better depending on the data set, as well as the problem type attempting to be solved. In conclusion, this project demonstrates how machine learning can be applied to real-world problems. While the models performed well overall, there is always room for improvement through better data and model tuning. This project provided valuable insight into the full machine learning process, from data preparation to model evaluation. Overall, it shows how machine learning can be used to generate meaningful insights from data. This concludes my final project for the class, so thank you for watching.